Hey everybody, and welcome to Number Theory Lecture 11. I have a special topic that I want to focus in on today, a lemma that we're going to be using quite a bit for the next week or so, or at least the consequences of this lemma we're going to be using quite a bit for the next week or so. Let's refresh our memory about an equation of this form. A, B, and C are non-zero integers, and there exists an integer pair, xy, such that ax plus by equals c, if and only if d divides c, where d is the greatest common divisor of a and b. Okay, but let's see if we can say this a little bit more coherently. We have non-zero integers a, b, and c, and we want to get a linear combination of a and b that equals c. A, b, and c, non-zero integers. We want to get a linear combination of a and b to equal c. And the theorem that we have tells us that this linear combination will exist exactly when greatest common divisor of a and b divides c. And we've seen that before in one form or another. We have a theorem that says the linear combinations of a and b are exactly the set of linear combinations of a and b is exactly the same thing as the set of multiples of the greatest common divisor d. So if this linear combination of a and b equals some integer c, then c has to be a multiple of d, the greatest common divisor of a and b. We're going to make quite a bit of use of this theorem, this fact, in the next week, week and a half. Here's a theorem. I don't think it's in our book as a theorem, but I want to spring this on you and take an approach that's not exactly the approach that our book has, but it will be an approach that is remarkably similar to something that we might have seen in our differential equations classes, where if we're finding a solution to a differential equation, we find a particular solution, and then we find a complementary solution, or a solution to the equation blah, blah, blah equals 0. A solution to this equation would be would correspond to our complementary solution in differential equations. We've also seen this approach in linear algebra, where we're getting the general solution to a system of linear equations. And again, we find a particular solution. Then we find the homogeneous system. That is where we have the system of equations all equal to 0 on the right-hand side. We add the two together and we've got the general solution. We're going to take that approach in number theory, where we're going to be finding general solutions to an equation like this And what we do is we're going to find the particular solution, and then we're going to find the complementary solution, the solution to this equation. We add the two together, we get the general solution. So the consequences of this theorem that we're about to look at are going to be important to us. Let A and B be non-zero integers, and let D be the greatest common divisor of A and B. Then the integer pair xy is a solution of the equation ax plus by equals 0 if and only if x equals b over d times t and y equals negative a over d times t for some integer t. We're going to make copious use of this fact. And in the next few minutes, we're going to prove this result so that we can use it in our next lecture. Okay? One direction, this proof is a snap. X equals b over dt and y equals negative a over dt for some integer t implies that ax plus by equals 0. Okay, suppose a and b are non-zero integers and that d is the greatest common divisor of a and b. Suppose further x is b over dt and y is negative a over dt. Just plug them in and let the algebra do itself. Ax plus by is a b over dt plus b negative a over dt, and that works out to abt over d minus abt over d. That's 0. Okay, no big deal. I hit the chicken switch. I did the easy part of the proof first. Now we'll do the converse. Okay, we're going back the other direction now. If a linear combination of a and b equals 0, that tells us x has to be equal to b over d times t, y has to be negative a over d times t for some integer t. A little bit trickier to prove this. This isn't automatic. And we'll remind ourselves of what our hypotheses are. Suppose that a and b are non-zero integers and that d is the greatest common divisor of a and b. And suppose further that our hypothesis is given. We have ax plus by equals 0. Now let's see what we can get from this. For lack of anything better to do, I'm just going to rewrite this and let's see, what is d? D is the greatest common divisor of a and b. So what does that mean? That implies that d divides a and d divides b. Okay. So I'm going to take this equation and divide both sides. Divide by d, a over dx plus d over dy is 0. And again, how should I say this? D divides A and D divides B. A over D and B over D are both integers. So what does that mean? A over D, x plus B over D, y equals 0. And A over D is an integer. B over D is an integer. That's going to be important. And we'll have, let's see. I don't have enough room down here, darn it. But note also, since D is the greatest common divisor of A and B, the greatest common divisor of A over D and B over D is going to be 1. So we have this equation, integer A over dx plus integer B over dy equals 0. And A over D and B over D are integers. Not only that, but A over D and B over D are relatively prime. Let me erase this board and see if we can finish this baby off. Okay, let's go into the home stretch. Here's our equation. A over dx plus B over dy equals 0. We arrange that. Just move this term over to the right. B over dy equals negative A over dx. Nothing earth-shattering about that. But remember, B over D is an integer, and A over D is an integer. And B over D and A over D are relatively prime. B over D divides negative A over dx, and we can just ignore the minus sign and say it divides a over dx. And this implies, let's see, what's the key here? B over D and A over D are relatively prime. So by Euclid's lemma, Euclid's lemma says if we have one integer dividing the product of two integers, and the divisor and one of these integers are relatively prime, that means the divisor has to divide the other integer. Okay. So we have B divides X. And what does that tell us? It tells us that X equals B over D times some integer, we'll call it T. Okay. Now this is half of what we wanted. We wanted to show that X has to be equal to B over D times T. We've got that. Now we have to show that Y equals negative A over D times that same integer T. And to get there, let's recall how we first started out. AX plus BY equals 0. That's where we started out. And why are we going back here? Because we're going back here now because we know what X is. AX, where X is B over D times T, plus BY is 0. And give me just a second to erase the board. I don't think I'll need much more than that. Okay. I am just going to take this term now and move it to the other side of the equation. So I have BY is equal to negative A B over DT. And I'm just going to rewrite the right-hand side here so that the important detail will jump right out at us. And maybe it's not jumping out at us right away. So I'm going to rewrite it again. And now it hits us right between the ears. There's a common divisor on both sides, B. And B is non-zero, so we can divide. And that tells us that Y is equal to negative A over DT, which is exactly what we wanted. So where did we start? Where did we finish? We started here, and with the hypotheses, we ended up here. X is B over D dt, and y equals negative a over dt for some integer t. We are going to use this lemma copiously for the next week and a half or so, doing what we call Diophantine equations.